Friends, today I will be talking on the last part of this unit, that is called enzyme inhibition. And you may be aware of this terminology. This terminology is very important in the enzyme chemistry, because you know that most of the drug discovery is based on this enzyme inhibition. Now, as you know that name itself is a definition. That means there are two terms. Inhibition, that means one type of molecule or substance that can inhibit, or you can call it is a alter the enzyme activity, because yes, it is one type of binding, you can call it. Second time, you know that there are a large number of pesticides and neurotoxic compounds. Sometimes that type of neurotoxic compounds do affect the active sites of the enzyme. Sometimes such type of compound is known as inhibitors. So first we have to study the types of the inhibition, and then there are different types of the inhibitors. And you know that there is a possibility that once that toxin or pesticides or molecule directly attack to the enzyme, and regeneration of enzyme is not possible. Maybe some covalent bonding. So that type of inhibitors is called irreversible inhibition. And sometimes regeneration of enzyme is possible. That is called that reversible inhibition. And of course, sometimes you know that the active site is very important, and they do bind with the active sites. There may be change in the conformation of the enzymes and like that. So, as you know, as I have already told you, that enzyme inhibition is very, very important, and there are many journals are also available on this concept, like Current Enzyme Inhibition, as well as the Journal of Enzyme Inhibition and Medicinal Chemistry. And I prefer this book because whatever I have prepared and I am just delivering to you, it is also based on these books, because you know that there are a large number of diagrammatic representations of that enzyme inhibition. So it is up to you that which diagram you should use. Okay, so there is no hard and fast rules, because there are a large number of very nice diagrammatic representation of this type of inhibitions in your course content. Pankha, I think you should open the fan and other things. So now let me first, actually it is a very broad chapter. If time permits, I will discuss, I will derive some of the derivation of this inhibition, but basically there are two types of inhibition. One is reversible inhibition, another is the irreversible inhibitions. And the definition is very simple. And this reversible inhibition can be divided into three parts. Reversible inhibition can be divided into three parts. One is competitive inhibitions. Very simple. That means there is a competition for the active site between the enzyme as well as the inhibitors. So that is called the competitive inhibitors. Now if you see carefully the Michaelis-Menten kinetics of these inhibitions, almost similar. But there is $1 million question in NET or ZRF or in our university system, because that is very important, that what is the possible effect of inhibitors on the two important parameters, Vmax, maximum velocity, as well as the Km. After knowing all these things, you are able to, yes, predict, yes, if it is a competitive inhibition, maybe the value of Km may be increased. I am not saying it is increase or decrease. And maybe there is no change in the maximum velocity. But sometimes what happens, if it is a uncompetitive inhibitions, maybe both Km as well as the Vm is also affected. So therefore, uncompetitive inhibition means there is no direct competition between the molecule, inhibitor molecule, and the enzyme for the active site. But what happened, that once that enzyme form a enzyme substrate complex, that enzyme substrate complex is bind with that inhibitors. So that is called the uncompetitive inhibitions. And last is called, sometimes it is called the non-competitive inhibition. And if you see the formula very carefully, I will explain that what is the actual meaning of all such type of the things. So competitive, uncompetitive and non-competitive inhibitions, most of the cases that is actually heavy metal pollution, heavy metals like mercury and other types of lead poisoning, and that will affect some of the sulfohydryl group of the enzyme. So it is not necessary that always they will attack the active sites. There are some other sites also, that is called the allosteric site and other things. So it is a non-competitive inhibition. So there is a possibility that enzyme also react with that inhibitor, not the active site but the other sites, as well as enzyme substrate complex is also affected. Now in addition to this competitive, uncompetitive and non-competitive inhibition, there is irreversible inhibition, and today I will not discuss all such type of things, and it is not necessary, because in this unit you see there is a lot of things. So just you have to study the fundamental concepts of the competitive inhibition and uncompetitive inhibition, so that if there is a possibility of any numerical problems or any multiple choice question, so you are able to answer all those questions. For that you have to understand the inhibition concept, otherwise it will be very difficult for you to reply the answer. So that is the importance of this subject. And of course there is some mixed inhibition is also there, partial inhibition is also there, substrate inhibition is also there, allosteric inhibition is also there, but I will not explain the details thing because time is limited. So I will explain the competitive inhibitions, and if time permits I will also explain the uncompetitive inhibitions, and then of course the non-competitive inhibition, because that is not properly mentioned in your prospectus. In prospectus only thing is that enzyme kinetics, enzyme catalysis, but without inhibition enzyme catalysis is incomplete. So therefore I am just doing all this type of things, and again you know that I am following that book of this Palmer, but you can follow the other books also, like Dixon and other things also. Okay, but final equations you are able to determine the final equations. And as I already discussed with you that many drugs are reversible enzymes, because drug discovery is very important, because you know in our biological system there are a large number of enzymes, and sometimes that we need some drugs to inhibit the activity of the enzymes, and the inhibitor enzyme bond is so strong that the inhibition cannot be reversed by the addition of excess of the substrate, and that Michaelis-Menten constant also depends upon the inhibitor concentration is also there. And because as I told you in my first part that we do a lot of work on this reaction of nerve gases with the most important enzyme, that is acetylcholinesterase enzyme. lot of kinetics we have done in our laboratory. So, as I told you that there are many beautiful diagrammatic representations available in the literature. It is one of the most simplest diagrammatic presentation of competitive inhibitions, and I have taken from this book. I have slightly changed these things. You know that there is a enzyme active sites and it is a substrate. So it is a competitive inhibition. So there is a competition between enzyme, the substrate and the inhibitors. And most of the cases, suppose we are using some enzyme succinate dehydrogenase. So if it is a competitive inhibition, so that inhibitor structure is very similar to that enzyme. You follow my point? If the enzyme is a succinate CH2CH2COH like that, suppose. So the inhibitor should be like malonate, like malonic acid form. So you know that there is a relationship between malonic acid and succinic acid. So that will be more reactive. So that will also affect this case. And if you, this is the most common example of competitive inhibition, most common example. That means the enzyme is, as I told, succinate dehydrogenase, substrate is succinate, and you can use the just malonate or glutarate or oxalate. You know, they are, all these inhibitors are structurally similar to that succinate. But if it is a non-competitive inhibitor, the system is entirely different. There, if it is a uncompetitive inhibition, so what I will do, that inhibitors will react with this ESI sometimes. So it will form ESI, or sometimes what happens, that enzyme is also react with these inhibitors. So one additional, in addition to Michaelis-Menten constant, we have to consider the inhibitor constant. Sometimes it is called the dissociation constant of EI or dissociation constant of ESI. This is the simplest example of competitive inhibitions, and this is available in all the books, everywhere it is available. Now this is very important. Before I do the derivation, now you know that there are many methods by which we can determine the Michaelis-Menten constant. And first, generally we do the role of velocity with respect to substrate concentration. So you know that this is the uninhibited Vmax, and it is with the inhibitors. And then for accurate determination of Michaelis-Menten constant, we have to use the Lineweaver and the bar plot, which is 1 by V0 velocity and 1 by S0. So we'll get a straight line. And on the basis of the straight line, you are able to predict, yes, this is the effect of inhibitors like that. After derivation, I will explain the things, that why, if it is a competitive inhibitors, Vx remains same and Michaelis-Menten constant is increased, because substrate bind enzyme so that the Vmax remains same while Km increases. And this is actually uncompetitive inhibitions, as I told you, that once it forms with this substrate enzyme complex, but it will not affect the active site. This is active site. There may be allosteric site or the other sites. So once it forms the enzyme substrate complex, but it will not affect that active sites, but it will affect that allosteric site. So we have to consider the inhibitor constant of this ESI in order to predict the role of inhibitors on the Km value and Ks value. And the example of uncompetitive inhibitors, again it is also available in the most of the books. Enzyme aryl sulfatase is inhibited by hydrazine. Second example is that inhibition of intestinal alkaline phosphatase using phenylalanine, and inhibition of lactate dehydrogenase by oxalate. Sometimes what happens in a multiple choice question that they have given the inhibition of lactate dehydrogenase by oxalate is an example of competitive inhibition, uncompetitive inhibition and non-competitive inhibition, like that. This type of possibilities are there. So in this inhibition you will see that Vmax as well as the Km also decreases. So after the simple derivation, then you can, if it is an example of the competitive inhibitors, so you can see that it is a line over and the bar plot, So the Km value is always greater than normal case, because this Km actually 1 plus I0 and then this inhibitor constant. So naturally, so I'll explain. Let me just so I use the YOLO, and sometimes some red is also there. So first I am doing the competitive inhibition. Very simple. I have taken E. First step is exactly same. You can see it actually, so that the student can also, you just once you set it, then you can see it. Yes, same thing. Second is that yes, product, and it is K2. But new thing is that this enzyme is react with inhibitors and it form EI. So we have to consider these things. Normally we take E0 normally. E concentration of enzyme plus ES, but here because enzyme inhibitor reaction, so we have to consider the EI. That is the difference between normal Michaelis-Menten kinetics and competitive inhibition. Just one addition term here. Number two, that it is just like normal case that applying the steady state approximation. But before that, you can write that because this is the slow step, so we have to consider rate is equal to K2 and E. Not at all difficult, but if you understand our first Michaelis-Menten kinetics is exactly similar. Practice makes a man perfect, so you have to do it regularly, so you can write any type of thing. So here is also same thing, you know, so many times you have solved it, that it is depends upon the again it is so applying steady state approximation, we assume that is equal to 0, so nothing. ES is equal to K1 ES divided by, that's all. And in some books also you can write that ES divided by E and S is equal to K, because K1, K2 divided by K1 is, you know, Km, so we can write the K. But the problem is that how do we determine the E? So what I do, because I know that this EI, we cannot ignore the dissociation of this EI, so EI actually, now here just see very carefully the difference between normal system and this competitive inhibition system is equal to E maybe, and that is Ki. This is called the inhibitor constant. Inhibitor constant. Is equal to EI divided by EI. So therefore, because we need the E, no sorry, we need the EI. We need the EI is equal to EI concentration of inhibitor divided by ionization constant of Ki. So I can simply use this EI that way. So E0 E red is okay. ES plus, you see, EI is equal to E I K I, or in some books you can write the EI also, inhibitor complex you can write. So therefore I can write like that. That means better to use this ink. E0 E1, just have decrease common, I inhibitor constant, you can bracket, you can write like that, Ki plus Es, isn't it? E0 is equal to E, just 1 plus I, Ki, Es. So we need the E actually, I say so. So E is equal to, direct I can write, because what I can write, E0 minus Es is equal to E1 plus I plus Ki. E0 minus Es is equal to this, so E is equal to, because we need the E0 initial concentration of the enzyme minus whatever the concentration of the Es divided by 1 plus I of the Ki. That's all. Last stage. So I have to substitute the value of E to our main equation. Then finally I need this rate and other things. So let me erase all these things. Because we have already solved it. Okay, last stage. So I have to write this value of this here. So just solve. Sometimes in examination, in last year, they asked this, they have given a structure and asked the student to derive the value of the Km. Last year if you see the question paper and other. So Es is equal to K1S K inverse 1. As I told you that it is up to you, that means I am using very simplest derivation on the basis of the Palmer, but as I told you that there are a large number of derivations, explanation, diagrammatic representation are available in different books, in different websites. So you can also use this thing, but this is the most simplest one. Therefore I am just following this equation. So what I am doing, I am just writing the value of here. So just I am using all these things. U0. It needs simple practice, no mathematical knowledge is required for that. You can molar concentration. In some books, as I'll explain this thing. So last stage, so ES is equal to what I can do, K1 S is 0. So K1, you know, E0 S. K1 S, K1 S, ES. K1 S. Now, once we get the value of ES, we have to substitute the value of. Now, before that, you can also solve one thing. What is that step? That means you can divide both numerator and denominator by K1. So you can write it as like E0S as well as the K you can write also. But I will write this after substituting the ES. I will write this final thing. So I will write the value of ES in this equation. So finally, rate is equal to, so K2 E0 S. Of course, K1 is also there. I think it is K inverse 1. Q1 or? Okay. No, it is K1. Plus, now you can divide it with K1. So this K1, you can. Divided by Q. And this is, you know, Km, Michaelis-Menten constant, and so I can write like that, K2E0 S divided by Km. Now you can understand why in competitive inhibition Km value increases, because Km is related, so that concentration of inhibitor is also included, as well as the ionization, the inhibition cost is also included. Whatever it is, naturally it is greater than 1, So 1 plus I up to Ki plus S. And you know that in some book it is written that, of course, it is actually this K2E0 is written as the V max, maximum velocity. You can write. And because substrate concentration is always greater than the enzyme, so sometimes we can write is also initial concentration, initial concentration, initial concentration. Like that, yeah, he is also right. So finally we get the rate is equal to V max S0 Km 1 plus I0 divided by Ki plus S0. But in order to determine the Km value precisely, so what we have to do? Double reciprocal plot. Just if we reverse this, that is called the Lineweaver and the bar plot. Lineweaver and the bar plot. Lineweaver and the bar plot. So that is 1 by rate. 1 by rate is equal to Km 1 plus I0, whatever, or you can simply write I, there is no problem, Ki divided by K2E0, or you can write V max, no problem. Plus K2E0, or you can write V max also, you can write. Also you can write V max. Or this whole part you can write Km dash prime or like that. It is up to you. And if you plot a graph Lineweaver and bar, I'll show you. One by rate, 1 by S0. Maybe suppose this is a normal cases, and so that is actually, so if I just calculate the slope, because 1 by rate and 1 by S, so the slope is equal to Km dash, not Km, Km dash or Km dash prime, because that includes this divided by Vmax. And in normal cases only Km divided by Vmax. But it is a competitive inhibitor, so it is Km dash, which is Km1 plus I0 plus Ki. So naturally, after deriving this, now you are able to say yes, in competitive inhibitors, the Km value is increases, but there is no change in Vmax. Now if I see that graph, so first graph you see that the normal cases and abnormal. Abnormal means in the presence of the inhibitors. Now I am not saying the inhibitor 1, inhibitor 2 and inhibitor 3. But in normal cases, if we plot this initial rate and the substrate concentration, initial concentration, so such type of thing. So there is no, if I just increase this thing, so you will get that there is no change in Vmax value. And because it is uninhibited, it is in normal cases, Michaelis-Menten constant, normal cases, and it is this K dash M or Km dash. When I just apply this Lineweaver and the bar plot, so 1 by V0 and 1 by, in normal cases, generally you calculate, last time I asked a question, how do you calculate the Km value with the help of the intercept and slope. So like that same thing. So same thing. Now I'll solve then uncompetitive, you will see that there will be slight difference. So it is slope is equal to Km and Vmax. But if we add some inhibitors, then of course the value of slope is the Km or Km dash divided by Vmax. Km dash is equal to, so naturally the value is increases. So is this type of numerical problem or short multiple choice question, but for that you have to understand this subject. Now my last question is that if I increase the inhibitor concentration, suppose in first case inhibitor 1, inhibitor 2 and inhibitor 3, so the slope will be slightly different. Inhibitor 1, inhibitor 2 and inhibitor 3. That means it is also worth studying to know the effect of inhibitor constant. So suppose I am just using 3 or 4 concentrations, so maybe like that, 1, 2, 3, like that. So it may be I3, I2, like that, I1. So now I'll try to solve the last part, that is the uncompetitive inhibitions. It is the competitive inhibitions, and you will see that nothing new, only thing is that we have to consider the inhibitor constant as well as the concentration of the inhibitors, whatever, in order to determine the Km value precisely and in order to predict the role of inhibitor on the Vmax value and Km value. And this is called one type of tailor-made of whenever a scientist do some work for some drug discovery, I will show after this lecture, I will show some of the values of Km and Ks from the other side. Due to copyright, I will not explain all these things, but these are also available in literature and in the book. Okay. Now the last part is the, let me just clean all. So it will take only 5 minutes. Now I am doing the uncompetitive inhibition. And in homework, you can solve the non-competitive inhibition also. But methodology is exactly same. Only difference is that here same thing. First part I will not repeat. Yes. Format. So same thing. But if it is a, so here ES that time plus I, so it is ESI. That is the only difference. And so quite natural, rate same thing, K2 and ES. So we have to substitute the value of ES. Same, here is also you know that ES is equal to K1 ENS. So it is also same, no new. Same thing, two part. Now what is the difference between this competitive and non-competitive? Difference is that same, that case E0 in place of EI. Now we will consider the ESI. So that is E is equal to E ES, whatever the concentration, and ESI. So like same thing, ESI is also dissociate ES and I. So in some book it is also written as KI, or if you specify it, so you can write also like that, K E subscript ESI, or that is terminology is same, inhibitor constant. So same thing. So this is ES exactly similar derivation, but when you get the final value, that will be different. That is the only difference. That will be different. Otherwise, and in order to learn the things, that why in the case of competitive inhibition Km value increases, and in some cases why Km value decreases, or in some cases there is no change in the Km value. So this is. So same thing like that. So ESI is equal to E0 is equal to E plus ES plus, you know that same. I am not doing any new thing. You can write KI or even KESI, it makes no problem. So just here only difference is E0 E plus ES 1 plus I, same, exactly same. So it is more simple, that E0 minus ES 1 plus I Ki is equal to E0 minus this part is equal to E. So substitute the value of E in our equation, first equations. You follow this point? Now I can remove all these things. It will take only 5 minutes. So K1 S same we'll write this E0 minus ES 1 plus I Ki. So K1 S plus first I will multiply this plus let me solve it, then we will discuss all these things. So it is last stage, rate so K2 same thing, K1 E0S divided by so numerator and denominator divided by K1. So K2 is 0 or Vmax E0 S divided by Km plus S 1 plus now see carefully the difference between these two competitive inhibitors and non-competitive inhibitors. So here you can write like that same thing, that K0 E S Km S like that. So if I apply the Lineweaver and the bar plot, so why my question is that in competitive inhibitors we have seen that the Km value increases, but my question is that what is the effect of inhibitor on Km for the uncompetitive, any guess, any idea about these things? Anybody can solve it. So what I do, just I reverse this, that is Lineweaver and the bar plot, just 1 by rate. So again here is also you can write Vm or whatever it is. One thing I can do, both we can write here Km Vmax and S. There are two ways. Number one way is that you can divide numerator and denominator by 1 plus I plus ki. Okay, you follow my point or not? What is now my objective is that I have determined the rate of the uncompetitive inhibition. Then I will plot a line over and the bar plot. I can write 1 upon rate is equal to Km S 1 plus Ki. Then it is the same, nothing new. But before that, I just want to minimize it. So what I do, I just want to minimize it. That divided numerator and denominator by 1 plus I plus K. So I will get this. Why the Km value will be decreased? Because this part will be V max S0 or S 1 plus isn't it? Km again divided by this is 1, this is I, don't confuse it. So that there is two terms. Now you can predict that what should be the effect of inhibitors. Suppose you are getting Vmax is equal to 5. 5 divided by something, some part is there. So it will be higher or lower. So that is both the Vmax as well as the Km. So I can write like that. I can write like that Vmax dot. You follow my point? Vmax divided by 1 plus I plus K is Vmax dot. Vmax dot. And of course S divided by Km divided by this, so it is also Km dot plus then whatever it is, S. So if I plot a line over and the bar plot, so same thing will be depends. That means you know that line over 1 by rate is equal to this. Km will be there. V dash max 1 plus K2 is a V max or like that. So what is the final conclusion of this uncompetitive inhibition? In competitive inhibition, you have seen that Km is equal to Km whole bracket 1 plus I plus Ki. That means the Km value is increases. Here Km is converted to Km dash. That means because it is divided by 1 plus, so the whatever the Km value in Michaelis-Menten constant, it is decreasing. Whereas in Vx, maximum velocity, that is also Vmax dash. So it is decreasing. So it is objective type question. Okay. So now I am just summarize all these things. And similarly, if you derive the non-competitive, I will not derive it because time is also there. Because there are two terms will be there. One is Ki, whatever it is, Kei, and another is Kesi. So your derivation will be much bigger than the uncompetitive inhibition. So in most of the examination, they do ask the Michaelis-Menten constant, and at the most they ask up to the competitive inhibition. So there is a very less chance for the asking the question of non-competitive or uncompetitive inhibition. But in multiple choice question, there is a absolute or short answer type question. Why in uncompetitive inhibition the value of Km and if it is a non-competitive inhibition, you see that is also when you derive it, I have derived competitive and uncompetitive. If I would have derived the non-competitive, then with the help of this diagram, I am able to discuss that there is no change in Km. There is no change in Km, but Vmax also decreases. And the example, as I have told you, that the heavy metal and other things. And in this inhibition, what I just derive it. In this inhibition, you have seen that both Vmax as well as the Km both decreases because that is divided by 1 plus we have to consider the concentration of inhibitors as well as the that inhibition constant. So that is the objective type of the questions. So, and in this case, first case, there is no change in the Km value, but there is Km value increases, but Vmax is decreases. So thank you very much. मैं एक दो डायग्राम दिखा के बंद कर दे रहा हूँ, आपका समय खत्म।